a matter of physics.
Hi everyone, we are students from Switzerland from the class 2MCZ. We know it's a horrible name, please don't laugh. We are going to do a physics project in class. That's why we are going to make videos about all the topics we are going to work through with Mr. Scherer, our lovely teacher, in physics lessons, and we hope they will help you to understand physics even better than you already do. And in this very first video of our channel Physics, we are going to explain the most important basics of optics. As an introduction, you can see the definition of light written in the middle. Visible light is electromagnetic radiation within a certain portion of the electromagnetic spectrum. So this is what Wikipedia tells us, and we bet you most likely don't get it. Don't be ashamed, because I didn't get it either and I won't ever get it. So we have formulated a more understandable definition sentence, which you see on the screen. Visible light is a part of the electromagnetic spectrum and is an electromagnetic wave. Therefore, it has the same speed as electromagnetic waves, 2.99 multiplied by 10 to the 8th power meters per second in vacuum. Light behaves like both a particle and a wave, and is, as we already mentioned, an electromagnetic wave. We may not see a visible light ray traveling, or we can follow its way by applying the following assumption, also called the ray approximation. Light always travels on a straight line path in a homogeneous medium, except if it crosses the boundary between two different materials. People interested in geometric optics do their work under the presumption of the ray approximation when thinking about the ways of light traveling and hitting different mirrors, media or lenses. So this next part will be quite important, so wake up and pay attention please. Something you should really remember after having watched this cool video is Fermat's principle, because it is a very important basic principle on which many rules are built, with which we are going to deal later. This main law says the path between 2 points taken by a ray of light is always the one which takes the least time. But never forget, this is not the same path as the one light could take as the shortest path. The next thing is, we repeat again, the speed of visible light is different in various media. But what happens if a light ray travels through two different media? On the first picture you can see absorption, but we are not going to talk about this phenomenon because it is not very important for this topic. And the second and third image show us reflection and refraction. The two may be the most important topics in geometric optics, which we are going to explain right now. Let's talk about reflection first, and you'll have to know the two laws of reflection for correct calculations. The incident, the reflected ray and the normal all sit in the same plane. The angle of reflection equals the angle of incidence. You can see this on your screen, and this is why reflection occurs. Light hits a mirror and gets reflected. And as you might have already known, there are many different types of mirrors. As the first one, we present the flat mirror. In the picture you see 4 different letters. I is a point and stands for the image of O, the object. For the U, the reflected rays appear to come from point I behind the mirror. The image we see can be real or virtual depending on whether or not the light actually passes through this point. If it passes through the point, it is a real image. If not, a virtual one. Note that flat mirrors always produce virtual images. P and Q are the image and the object distance, respectively. Their value is the same, but they appear on opposite sides of the mirror. Another characteristic of the image formed by a flat mirror is that it is apparent left-right reversal and is unmagnified and upright. But if we take a curved mirror, everything we've told you in the past few minutes is different. This type of mirror has a radius and a center of curvature called R and C, because the mirror is shaped like the segment of a sphere. Minus QF, the focal distance, is simply R divided by 2, and capital F is the common point where parallel incident rays that falling close to the principal axis meet. This is the reason why there are parabolic mirrors, of which we are going to talk later. There are 2 types of curved mirrors. The first one is the convex mirror, and its opposite is called concave mirror. In this one you can see the reflections on the inside. If you want to draw the image a concave mirror creates on paper, you have to consider the following 3 construction rules. Ray 1 is drawn parallel to the principal axis and gets reflected back through the focal point F. The second one is Ray 2 is drawn through the focal point F and reflected back parallel to the principal axis. And the last one is Ray 3 is drawn through the center of curvature C and reflected back on itself. Wherever 2 of any of these rays meet in a point, you can draw the image, and the third ray is only drawn to check the construction. For a convex mirror, these rules are exactly the same, just like the following formula, which we call mirror equation. 1 over P plus 1 over Q equals 2 over R. Based on this equation, you can derive more rules like 1 over P plus 1 over Q equals 1 over F, or Q equals P multiplied by F divided by P minus F. For the magnification of the mirror, you can use the following equation. M equals H prime over H, or negative Q over P. The only important difference between convex and concave mirrors, which you should note, is that F and C lie on opposite sides. So this was a lot of formulas. The last part with variables is yet to come. After that, you don't have to deal with this stuff anymore. Let this be kind of a motivation. So, to avoid incorrect calculations, follow the conventions you can see in the table. The signs are very important. Be careful with them. We will show an example so that you understand it better. At this example, this candle which we have shown you a few seconds ago, the radius of curvature and therefore also the focal length both lie in front of the concave mirror, so they are both positive. Also, the image distance is positive because the image appears at the front of the mirror. But the image is inverted, therefore the image height and magnification are both negative. So if you struggle with the signs, take a screenshot of your table. But be aware, your teacher won't allow you to use this during your exam. Well, unless he's an angel who forgives you for your non-existing ability to know all these conventions by heart. But let's forget those nasty teachers and return to the subject. The small piece of extra information is the front side of the mirror is where light rays incoming parallelly to the principal axis propagate, and therefore the other side is the back side, where virtual images are formed. This may sound obvious, but beware later, when we are going to talk about the lenses in our next video, this will be quite different. We've mentioned the spherical mirror before, maybe you can remember. In that case, only rays of light which are close to the principal axis pass through the focal point. To solve this problem, parabolic mirrors are constructed. A parabolic mirror doesn't have a center of curvature anymore, because the radius of curvature is different for different points of the mirror. Maybe you also can remember Fermat's principle, which we have mentioned before, and which is, we repeat ourselves, an incredibly important thing, because it's the underlying principle of refraction. If you can't remember, don't worry, we will repeat it for you because we know exactly how this feels. The path between 2 points taken by a ray of light is always the one which takes the least time, and not the shortest one. In the following example, the light ray from a light bulb travels to the fish. Therefore, the light ray has to pass through 2 different media, namely air and water. Most people, maybe you too, would presume that light travels in a straight line to the fish, but sadly that's wrong, because light travels faster in air than in water. Therefore, it looks approximately like this. If the speed of light is faster than in the first medium, the angle of incidence is bigger than the angle of refraction. And if the speed of light is slower in the first medium, the angle of incidence is smaller than the angle of refraction. Based on this phenomenon, we think that the fish lies somewhere on a straight line corresponding to the light ray that hits our eye. But we don't want to sketch the rays only, we want to calculate the exact values. I mean, maybe it's like this only because your teacher wants you to calculate around, but we will tell you anyways. For the calculation, we need the law of refraction with the following formula. V1 multiplied by the sine of theta 2 equals V2 multiplied by the sine of theta 1. The V's represent the speed of light in the 2 different media, and the symbols theta stand for the corresponding angles. If you wonder what sine is, it is one of the trigonometric functions. You can also see it on your calculator. Now, as the next one, we introduce the index of refraction n of a medium. It's defined by the following formula. N equals the speed of light in vacuum over the speed of light in the medium, so n equals c over v. The higher the index of refraction of a medium, the more time light needs to go through this medium. Therefore, the higher the difference between the indices of refraction of two media, the bigger is the difference between the two angles. Now we can construct an alternative formula for the law of refraction if we replace the velocities with the corresponding indices of refraction. n1 multiplied by the sine of theta 1 equals n2 multiplied by the sine of theta 1. Even though refraction isn't part of that incredibly difficult French grammar we have to deal with in school, it has an exception, which is called the absolute or total internal reflection. If light is coming from an optically denser medium, like M1, and hits an optically thinner medium, like N2, the angle of refraction will be bigger than the angle of incidence. If we increase the angle of incidence so that the angle of refraction approaches 90 degrees, we will notice that we won't reach 90 degrees. There will be an angle of incidence at which the refracted light beam just will disappear, and this angle is called the critical angle of absolute internal refraction. We can calculate it with the following formula. Theta 1 equals the arcsine of n2 over n1 in brackets. Remember that the index of refraction of the first medium has to be bigger than the index of refraction of the second medium. So in a very short summary, if the angle of incidence is bigger or equal to the critical angle, there is no refraction anymore, but only reflection. This phenomenon is called total internal reflection. And that's it. Now you have learned a lot about optics. If you are able to explain Firm's principle, reflection and refraction, you are a genius. If not, just watch and listen to the parts you can't remember again. The content of the topic is really dense, but very important and also quite interesting once you understand it. And if you have any questions, we will do our best to answer them in the comment section below. Also, don't forget to check our Instagram. Enjoy your studying, and we hope it's not still dying. Have a good time. Bye.